Hi Technisci fam, thanks for joining me in the second video on beams. I'm looking at cantilever beams in this one, and I'll be taking you through how to get the reactions, how to do your shear force diagram and your bending moment diagram. I have a bonus. I'll be showing you how to determine your max bending moment. You really don't want to miss any aspect of this video. So make sure you tune in to the end, and if you miss any part of it, just simply pause and replay. Just as easy as that. So before we get into doing the question, I'm going to be showing you a little description and a sample of what cantilever beams look like. A cantilever beam is one in which one and only one end of the beam overhangs the reaction. Now, this can be shown in two ways. One where you have two reactions and only one end overhangs, or another where only one support is there where it's a fixed end and then the remainder of the beam is overhanging. Now, for BMed and doing these nature questions, you will mainly work with questions that have two reactions, and again, cannot say this often enough, being that it's a cantilever beam, only one end will overhang the reaction. Hope you got that. And so now you are ready to go into the question. So this is a question that we're going to be working on for this video, and it is a cantilever beam, and we know it's cantilever because only one side of it has a portion of the beam overhanging the support. Now, sometimes you may hear it being referred to as an overhanging beam as well. It is a type of overhanging beam, but it can be specifically referred to as a cantilever beam. So let's see how quickly we can get through this question. So first step is, of course, to draw our beam. And when we are drawing our beam, we have to ensure that we represent the spaces to an appropriate scale. So the space distances are 3 meters, 5 meters, 6, and 4. And so I think I'm going to be using the scale 1 millimeter to represent 1 meter. So what I'll do, I'll draw each space separately so that it is easier for me to locate the arrow location. And arrows can be pretty easy to draw. I use polyline and I use half width. I use polyline and I use half width. Then I'll just copy these and put them along the beam. So I'm just using the mirror command to get the reactions. So there I have my beam represented now. So of course, it's always a good practice to just check to ensure that your spaces are correct. I remember you can use whatever scale is convenient to you. You could have chosen to use a scale of 10:1, whatever scale is convenient to you. And so now I'm just going to label. So I'm just going to copy the labelings from the original one to save some time. So now we're going to move on to our next step, which is to label our spaces according to Bose notation. Okay, so now we have our spaces labeled. Excellent. So I'm now going to be putting in the scale. Just moving this over a little bit so I have some space. So now we're going to move on to doing our load line, which, as we know, represents the loads that are acting on the beam. So for this one, we have 3, 5, and 2. And again, I'm going to be using a scale of 1:1 that is convenient for me. And again, I draw them individually so that I can easily locate the ends of it for my polar polygon. So I'm going to label before I move on any further. So remember now, when you are using Bose notation, each member, each load that is acting on the beam can now be given a different notation. to easily identify it. So this load is AB because it's between space A and B. This is BC because it's between spaces B and C. This one is C and D. So this is CD because it's between those spaces. This member is DE, and this one would be EA. And remember, you go in a clockwise direction when you are using Bose notation as well as when you are naming your members. So I'm going to now be labeling them on the load line. Remember, on the load line, it's a common letter, but when you're labeling spaces, it's a capital letter. So you will see that I like to do a lot of copy because it really speeds up the time. So at first, you will not be representing your reactions. You are going to have to determine those. So what you are representing are the members that are acting downward on your beam. So we have AB, BC, and CD. Those are the only members acting downwards. So I'm now going to be putting in my point, PO. And I'm just going to choose a convenient point. Now, this is not the exact center of the load line, but I'm going to be using that as my reference point. I'm going to be using tracking, and I'm going to be putting it 5 out based on my scale. And you can choose, let's say you were using 10 to 1, then you could have used 30 or 50. It's really up to you. And then I'm going to now be connecting lines from each end of my load line to the pole. So remember that point now that we just drew is our pole. So now we have a polar polygon, and I'm also going to be putting in my scale as well and my labels. So again, copying, making life easier. And you have to ensure that you're using correct units. So for loads, it has to be some newtons, either kilonewton or newton. For your space diagram, you are scaling the spaces, and so it will be millimeters to meters, something of the sort. So now that we have that, we're now moving on to our next step. So our next step is to draw, and I'm going to be using what I have as a hidden line, is to draw horizontal lines from each point on my load line, and just make sure that it extends beyond the given beam that we have drawn. And then we're going to be drawing vertical lines from each line of action of our load. And I want it to go a little bit further down because I'm going to be putting a diagram down there, or a link polygon. And of course, again, gonna copy. Kind of speed things along. So there I have my horizontals and my verticals. Now, if you want your lines to not have the spacing being that big, you can reduce your line type scale. So let me select one of these, go to properties here. And then you can change your line type scale. Let me just widen it so you can see. And you can reduce it, and it will have that effect. So if you prefer to see your lines a little bit smaller, then you can adjust the scale. And then I'll just use match properties, and I will match all of them to that property. And there you have it. So now we're going to be continuing. So I'm going to use different colors here so that I can show what exactly is happening. You can follow along with the color codes that I'm using. So I'm now going to getting our link polygon, and we do that by transferring parallel lines from our polar polygon down to the spaces, and I'm going to be showing you that now. So this line, and let me put in O, didn't put in O earlier. Turn off ortho for a second. And I'm labeling O, which is my pole. So now I'm going to be copying line AO because I need to get a parallel line. So I'm copying line AO, and I want it to go within the space that represents A, which is the space between these two lines, as you can see from our space diagram. So I want AO to go between that space. I'm copying it, putting it at any convenient point. Didn't have to put it at midpoint just now. And then I trim it off to ensure that it only fits within the space that it represents. Then I'm going for BO, copying it again, putting it in the space it represents, B. And let me try to extend or trim, whichever works, so it seems to fit exactly within that space. Then I'm going to copy CO, and C spans this entire distance. You have to be careful to not mix up C. Ensure that all the members are spanning the correct space or distance that it should. So I'm putting in C now, and I hope you're following my color code for the lines. So C went all the way there. Wow. This is a little bit different from what we would have done before, but never fear, we can get this done. Then I'm going to be copying DO, and DO should fit in the space D. So it's quite simple. I'm copying it from this end this time because the polygon went there. And I must continue the polygon one side after the other. So that now becomes the D. So I need to trim it so that it only spans the space D, which is right here. So now my polygon is almost done. It's now open, and I need to close my polygon. So what am I going to do? I'm going to take a line. I'm going to make it my object layer, but then make my line type hidden. Let's use hidden too. And I'm going to be closing my polygon. So that now represents the closing side of my polygon. And I'm going to just be labeling each member so that you can follow. Okay, so now I've labeled AO, BO, CO, and DO. I need to know what would be the name of this member. So you simply look on your space diagram and figure out what space this member spans, and it spans the space E. So that simply means this now becomes EO. And now what I do, I copy this final one and put it over on my polar polygon. Trim it off. And now this is representing member E. So I can tell you that by now you would have had the reactions for your beam. How do you go about getting that now? I am going to be dimensioning. I'm just going to use a little match properties. Good. So, and then I'm going to use continue. So now what I have, this reaction is now DE, and so it spans from the distance D up to E. So we have it at 6. Because I use a scale of 1 to 1, then there's no conversion for me to do. So I know that this 6 is representing 6 kilonewtons. And for my second reaction, it's EA. So we go from E up to A, it is 4. And it would therefore represent 4 kilonewtons. Hope you got that. And that would be how you would have gotten your reactions if that's all the question asked you to do. So now I'm going to just be writing that so that we can present our answers carefully or properly. So I've now noted my reactions, and I can write them like this because I have no conversion to do. So it is EA 4 kilonewtons, DE 6 kilonewtons, and that would be our reactions. So now we're going to continue, and I'm going to be showing you how to get your shear force diagram as well as how to determine your max bending moment. So I just want you to note, you may have recognized that the lines have gone. You are no longer seeing your hidden lines. It's a simple matter of just changing your properties. But you don't need to continuously do this because I will show you that once you go to plot, the scale will still be showing. So you're still seeing that this one is looking like a solid line here. Once we get into our paper space to print, then it would be represented according to the line type it is. So let me just quickly show you that and come back. So here you're seeing that the lines are still visible. They're still showing broken. But if when you come into your paper space, it's not visible, you just adjust in the same manner. So now we are going to do our shear force diagram. So for our shear force diagram, what we will do is to draw horizontal lines within the spaces on the respective horizontal lines. So for instance, this is space A, and I'm going to be drawing it on the line, horizontal line that represents A. Now, when we get here, we're seeing a member, a load going down. We go down and it goes to B, so then we go across in B. Get here, it goes down to C, across to C. C doesn't stop here, all the way over. Then it comes down to D. And I'm going to pause right there because this is the part that sometimes poses a little challenge. Now that we added our closing side to our polar polygon, we now need to go in and add that horizontal line to our diagram. Now, as I said in my previous video, and if you haven't seen that video, I'll put the link in the iCard as well as in the description. What I usually do is put in this horizontal line after I would have done the other loads, after I've done the loads, so that there is very little chance that there will be some error. So I don't usually put that in at first. So I'm now going to continue my shear force diagram. So I was now at D, and D spans this space, so I come across in D. Then when I get here, it goes up, and it's going up to E, that line I just put in. Then it goes all the way across here, and then from here up. And that is where our shear force diagram would be completed. So let me now turn on my line weight so that you can see the diagram and what it's looking like. So this now is our shear force diagram. And I'm going to be putting a point to indicate the portion where shear force would be 0. So the point where our shear force is usually 0 is, in simple terms, where the line that is running between our reactions, this line here, where it intersects a vertical member from the loads. That's more or less where you will find it. You will have situations where it may be different, but generally that is how you locate it. So I'm just going to finish labeling my shear force diagram, and then I'm going to be showing how we calculate maximum bending moment. Okay, so there we have it. And now, final thing that we're going to be doing in this video is to determine what our maximum bending moment is. So I'm now going to take you through steps of how to get your max bending moment. So the first thing you need to do is to write your space diagram scale in 1 millimeter to a whatever meter. For us, in this example, it's easy because our scale is already in that way to show what 1 millimeter represents on the scale. So we could do that. So our example, it would be 1 millimeter to 1 meter. Now, if you were using a scale of 10 millimeters to represent 1 meter, then you would have to divide both sides by 10. So you would end up have 1 millimeter, because for you to get from 10 millimeter to 1, you have to divide it by 10. So you would then have 1 millimeter would be equal to 0.1 meter. If you need help with this part in particular, just send me a message in the chat and I'll do a video just for this. So after we've done that, we're then going to write the load line scale in 1 millimeter to B Newton. So in the same manner. And again, for this example, it's pretty easy for us because we already have it in that manner. So we already have it starting with 1 millimeter, already showing us what 1 millimeter represents for the scale. So we're good. Next one now, you would measure the distance of the pole and record that as C millimeters. So I'm just going to dimension. And then of course match properties. All right. And the final aspect of our formula, which is D, is to measure the height of the max bending moment section, and that will become D millimeters. So we did say shear force is 0 along this line, and so we're going to measure the height along this line. So that is 3. So our A is 1, our B is 1, our C is 5, and our D is 3. Formula time. So now our max bending moment is A times B times C times D. Simple as that. So now I'm going to edit. And the unit is kilonewton meters. So let me just quickly label my diagrams and then we wrap. So there you have it. We have our given question here. We went and we did our space diagram with our space labeling by Bose notation. We have our load line and our polar polygon, our shear force diagram, and our link or funicular polygon. And then we did our calculations for our bending moment. Have you liked this video as yet? How about subscribing? Was this content helpful? Then if it was, please make sure you share the love so that others can benefit from this video. So now I just wanted to highlight a little adjustment that can be made. Now previously doing the question, I would have had my precision for my units set to, I would have had my precision for my dimensions set to 1 decimal place, and let's do that again. And I would have gotten my reaction as 4 here. But if I adjust it to 2 decimal places, to 1 decimal place, then I would be getting 3.9. Now what that will do is just change the answers to a little bit more precise, but it will not be of such that it will cause you to get it totally wrong. So having my reactions with 1 decimal place, I would have gotten 3.9 and 6.1. And then for my max bending moment, I would have gotten 3.3 here, and that would make my answer here 16.5. So I just wanted to highlight that just in case anyone is having any concern. Now let me also say, even if your link diagram doesn't look exactly like mine, or your polar polygon isn't looking exactly like mine, I guarantee as long as your procedure is correct, you will be getting these answers as well. Try it out and let me know if you did get the same answers for the reactions and the max bending moment. Thank you for watching to the end. I hope this video was very informative. I hope it was helpful. And more importantly, I hope you were able to follow through to the end. Now, again, make sure that you check all the videos that I post in this series so that you set yourself in a position to totally master this concept. Thank you again for watching, and remember to like and share. Leave a comment in the chat below so that I can know how this video was for you and if you need me to do any specific video on this topic. Thanks again, guys. See you in the next one.